So we will now discuss the rest of the properties of Fourier transform. So do not give much credence to the numbering of the properties here. The duality property states that if x of t has got a Fourier transform given by x of j omega, you can also represent this as x of omega, as we have seen. Then capital X of t will have a Fourier transform given by 2 pi x of minus j omega. You can also write this as 2 pi x of minus omega. So I will use the whiteboard to illustrate this property to see what this property means. So you have x of t is Fourier transformable to, I'll write this as x of omega. So x of t has some shape, capital X of omega has got some shape. Then capital X of t, which is a time domain function having the same shape as x of omega, except that omega is replaced by omega is replaced by t. Now that will have a Fourier transform given by 2 pi x of minus omega. So x of omega has got the same shape as x of t, except that the variable t is replaced by the variable omega, and now that is mirror reflected with respect to the y-axis. So for example, if you have a Fourier transform, if you have a signal delta t, then let us try to find out the Fourier transform of delta t. So we'll just write the Fourier transform of delta t as integral minus infinity plus infinity delta t e raised to minus j omega t dt. So this will sample e raised to minus j omega t at t equal to 0 as per the shifting or sampling property of the impulse function, and this will give rise to the value equal to 1. So this means that the Fourier transform of delta t in the time domain is given by 1. So 1 is a constant from minus infinity to plus infinity. So this value is equal to 1 for all frequencies. So what does it mean? If you add up all the frequencies from minus infinity to plus infinity with the same strength equal to 1, then you will get delta t. So delta t, that is the impulse, contains basically all the frequencies, every frequency with the same strength. So this is the spectrum of delta t. Now let us look at the dual of this relationship. The dual states that if you have capital X of t, which means capital X of t would be this time function 1, and this is t, this is capital X of t. So this is Fourier transformable to 2 pi into x of minus omega. Now here that would be delta of omega, and delta of minus omega is same as delta omega, and you have to multiply this by 2 pi. So therefore this becomes the function with area 2 pi located at omega equal to 0. Okay, so this is omega. So here, because this delta t is a symmetric function with respect to the y-axis is here. So if you reflect this with respect to the y-axis, you will get the same function. So here you have delta t is Fourier transform to 1. So 1 in the time domain is therefore Fourier transform to 2 pi into delta of minus omega, which is equal to 2 pi into delta of omega. So this is as per the duality theorem. So this is the statement of the duality theorem. Now we will prove the duality theorem here. So the proof is very trivial and straightforward. So from the synthesis equation, we can write x of t is equal to 1 by 2 pi integral minus infinity to plus infinity x of j omega into e raised to j omega t d omega. Cross multiply and write 2 pi x of t is equal to integral minus infinity to infinity x of j omega e raised to j omega t d omega. And if I replace t by minus t, this becomes 2 pi x of minus t is equal to integral minus infinity plus infinity x of j omega into this will be e raised to minus omega t, because we replace t by minus t. Now just interchange the roles of t and omega. So that will give you 2 pi x of minus omega. You can skip this j here if you do not want this. So 2 pi x of minus omega is equal to integral minus infinity plus infinity. Instead of omega, you will have x of t e raised to minus omega t dt, which is the Fourier transform of capital X of t. So in other words, capital X of t is Fourier transform to 2 pi x of minus omega. So this is what we have proved now. Now let us try to find out the Fourier transform of the unit step function here. Now this is approached in a very different manner. So here we have some peculiarity. Later we will see the relationship between Fourier transforms and Laplace transforms. So we will discuss Laplace transforms once we discuss the Fourier transform completely. So Fourier transform is very closely related to the Laplace transform. So Fourier transform, the variable is omega, and in Laplace transform, the variable is s. And you would have studied this in engineering mathematics as a complex variable, which you can write as sigma plus j omega. So say for example, if you have x of j omega, so this you can generally write that. So I repeat and emphasize the word generally. You can generally write as x of j omega as equal to x of s at s sigma is equal to 0. So if I put sigma is equal to 0, so let us draw a two-dimensional complex plane. So sigma being the real axis, j omega being the imaginary axis. And so this is basically the S plane. We call this as the S plane, which is a complex two-dimensional plane. And you plot h of s or x of s as a surface plot on this two-dimensional plane. So at each and every point you will have a height. So maybe at this point you will have a height. And you have at this point another height. So this basically will constitute a three-dimensional structure, which you can think of as projecting from the screen, projecting outwards from the screen, or maybe even inwards, depending on h of s having positive or negative values. So anyhow, this h of s is a function of sigma plus j omega. And if I put sigma equal to 0 as here, it means that you are looking at h of s along the j omega axis, or in other words, you can think of taking a slice of the three-dimensional structure on the j omega axis, just like a knife slices a cake. You can think of a knife slicing x of s on the j omega axis, and the values that you get over the j omega axis will constitute x of j omega. But that is in general. In general, you can say x of j omega is equal to x of s. But there are several exceptions where this is not true. And one example that we are going to see is the unit step function u of t. So the Fourier transform of u of t is not derived in the conventional manner. So that has to be very carefully understood. The Fourier transform of u of t is found out in a somewhat different manner. So first of all, we write x of t as equal to a combination of an odd function and an even function. So this we have previously seen that any function x of t can be written as a combination of an even function xe of t and an odd function x of t, where the even function xe of t you get by adding x of t and x of minus t by 2. So x of t plus x of minus t by 2. So you can see why it is even, because if I put t is equal to minus t, so you will get this as x of minus t plus x of t by 2, which is same as equal to xe of t. So this is equal to xe of minus t. So this is an even function. Likewise, I can define an odd function. X of t is equal to x of t minus xe of minus t by 2. And you can see that this will be equal to minus xo of minus t. So it's very easy to prove. So any function can be represented as a combination of an even function and an odd function. Any function can be represented as a function of an even function and an odd function. Likewise, let us look at u of t. So the even part of u of t would be equal to u of t. Even part is equal to u of t plus u of minus t by 2. So let us draw this. U of t would be this 1, and u of minus t would be this part, like this part, because it is reflected part. And so that is 1 throughout. U of t plus u of minus t would be 1 from minus infinity plus infinity. And you have to divide this by 2. So this would be equal to 1 by 2. So this height is equal to 1 by 2. So this is the even part of u of t. Likewise, you can write down the odd part of u of t. Odd part would be u of t minus u of minus t minus u of minus would be like this. And you have to divide this by 2. So this is 1 by 2 and this is minus 1 by 2. And the odd part you write as equal to, even part is 1 by 2, odd part is equal to 1 by 2 into, you introduce a new function called signum of t. 1 by 2 into signum of t. So odd part is 1 by 2 into signum of t, where signum of t is a function given by 1 for t greater than 0, and it's equal to minus 1 for t less than 0. So these are the even and odd parts of the unit step function. So xc of t is equal to 1 by 2, x of t is equal to 1 by 2 signum of t. And let us look at the second function, x of t is equal to 1 by 2 signum of t. And we'll write z of t is equal to signum of t. Z of t is equal to signum of t. So let us write down the derivative of signum of t. So let us see what happens when you take the derivative of signum of t. So signum of t is again this function. This is signum of t, 1 and minus 1. So which we can approximate as we have seen for the unit step function, you can approximate this as this by a linear transition between the positive and negative half. So this is 1, minus 1, and this is plus 1. And let us consider this width as equal to a. And we will let a tend to 0. And if I take the derivative of this function, let us see what happens. If I take the derivative of this, what is the slope of this line? This is 2 by a. So this height would be 2 by a. And this width would be equal to a. And if I let the derivative of this, so if I let a tend to 0, 2 by a will tend to infinity, a will tend to 0. And therefore, what? So if I take the derivative on both sides, you can write d by dt of sigma of t is equal to 2 delta t. So d by dt. So if I let a tend to 0, this will tend to limit a tending to 0 will give you this function. The height is 2, this is 0, and this is a function t. This is the variable t. So this is t. So you have d by dt of signum of t is equal to 2 delta t. Now what we will do is we will apply the differentiation property of Fourier transforms. So if we have written signum of t is equal to z of t, right? So signum of t is equal to z of t, and you have d by dt of z of t will be Fourier transform to, what is d by dt of z of t Fourier transform to? D by dt of z of t would be Fourier transform to j omega into z of j omega. So this you can write as j omega into z of omega. Or in other words, you can write z of omega is equal to 1 by j omega into Fourier transform of 2 delta t. So that is what we have here. You have j omega. So if I take the Fourier transforms of this equation, j omega into z of omega is equal to 2, because delta t has got a Fourier transform given by 1. So j omega into z of j omega has got a Fourier transform given by is equal to 2. That's the Fourier transform of this is the Fourier transform of this expression. Fourier transform of d by dt of sigma of t or d by dt of z of t can be written as j omega z of j omega is equal to 2. Or in other words, z of omega is equal to 2 by j omega. So what does this mean? What does this mean? Therefore, 1 by 2 sigma of t is Fourier transform to 1 by j omega. And applying the linearity property, then u of t would be half plus half sigma of t is therefore Fourier transform to. Half is Fourier transform to, as you know, 1 by 2 is a constant. 1 is Fourier transform to 2 pi delta omega, as you know. So therefore, 1 by 2 is Fourier transform to pi delta omega, and 1 by 2 sigma of t is Fourier transform to 1 by j omega. So this is pi delta omega plus 1 by j omega. Pi delta omega plus 1 by j omega. So as we had seen earlier, this is a special case. Let us write down the Laplace transform of delta t. So that will be integral minus infinity to plus infinity delta t e raised to minus st dt, because we already seen this in some engineering mathematics papers. So this will be sampling from the shifting property of impulse function. It will be sampling e raised to minus st at t equal to 0. So this will be equal to 1. And you know, integral minus infinity to plus infinity u of t into e raised to minus st dt would be equal to integral 0 to infinity e raised to minus st dt, e raised to minus st dt, and this will be equal to 1 by s, right? So this is how you find the Laplace transform of functions. So if I evaluate this, this will be e raised to minus st by minus s between limit 0 to infinity, and that will give you 1 by s. You can evaluate this to see. Now, as we have seen for general cases, for generally you can write x of j omega is equal to x of s for sigma equal to 0, or in other words, replace s by j omega. So if I replace s by j omega, this would only be 1 by j omega. This would only be 1 by j omega. But you know that the Fourier transform of the unit cell is not equal to 1 by j omega. Instead, you have this additional term of pi delta omega plus 1 by j omega. So this is the additional term. So this property that the Laplace transform evaluated over the j omega axis will give you the Fourier transform is not satisfied for this unit cell function. So this is a peculiar function. This you have to remember. Now we'll move on to the integration or accumulation property of Fourier transforms. This uses the previous result to prove. So the accumulated or integrated value of x of tau d tau from minus infinity to t. So what does it mean? So what we have here is, again, we will have a pictorial representation to have a finer understanding of this. So let us consider an x of t. So this is the time instant t. And let us say you have your y-axis somewhere here. So this could be either positive or negative. So if I evaluate the value, so this is tau, and this is tau equal to 0. So this is a time instant t, some arbitrary time instant t. So if you evaluate the area under the function from minus infinity to some time instant t, so that you can write as integral minus infinity to t x of tau d. So that is the area under the function from minus infinity to t x of tau dt. So this is x of tau. So this function is x of tau. So maybe this function continues like this. So the integrated summation, integrated value of x of t from minus infinity to t is Fourier transform to 1 by j omega into x of j omega plus pi x of 0 into delta omega. So we have to prove this now. So proof is again very simple, observing that integral minus infinity to t x of tau d tau is equal to integral minus infinity to plus infinity x of tau into u of t minus tau d tau. Why? This we can write this as x of tau into u of t minus tau. Why? because you can write u of t minus 2. If this is 2, u of t minus 2 would be this function. If this is t. So this is equal to 1 from minus infinity to t. So t can be both positive and negative. So if I multiply x of tau by u of t minus 2, basically I am looking at the values of the function from minus infinity to t. Right? So therefore you can write this as equal to integral minus infinity to plus infinity x of tau u of t minus tau d tau. X of tau u of t minus tau d tau. Okay. So this you can write as x of t convolved with the u of t from the definition of convolution. Now you will need to look at what is convolution here and what is the Fourier transform of convolution of two sequences. So let us look at convolution of x of t and h of t. So x of t convolved with h of t, you will prove that it is equal to the product of the individual spectra, that is x of omega into h of omega. So the proof is trivial. So we'll write the Fourier transform of the convolution of x of t and h of t as here. The Fourier transform of integral minus infinity plus infinity x of 2 h of t minus 2 d 2. We can write this as integral minus infinity to plus infinity of this convolution integral multiplied by e raised to minus omega t dt. So we will rearrange the integral as follows: integral minus infinity plus infinity. I will take x of 2 outside and evaluate this with respect to t first and then 2. So this is integral minus infinity to plus infinity h of t minus 2 e raised to minus omega t dt, which is the Fourier transform of h of t minus 2. Now if you assume that h of t has got a Fourier transform given by h of omega, we will apply the time shifting property and write this as h of omega into e raised to minus omega tau. So here you have integral minus infinity to plus infinity x of tau h of omega e raised to minus omega tau d tau. I'll take h of omega outside the integral and write this as integral minus integral h of omega into integral minus infinity to plus infinity x of tau e raised to minus omega tau d tau. Now this is a definite integral. I can put any dummy variable that I want, t or tau or lambda, whatever, because it evaluates to a finite integral. We will call this as x of omega because this is the Fourier transform of x of t. So this therefore equal to x of omega into h of omega. So this is the result. That is, if I convolve two functions in the time domain, then in the frequency domain, it's a multiplication of the individual spectra. So we'll use that result here. So x of t convolved with the u of t, as we have a result here, can be written as equal to Fourier transform of having a Fourier transform into Fourier transform of x of t into Fourier transform of u of t. We have found out the Fourier transform of u of t here, which is pi delta omega plus 1 by j omega. So therefore, this we can write as x of omega into pi delta omega plus 1 by j omega. X of omega into pi delta omega plus x of omega by j omega. Now, pi delta omega into x of j omega, it samples x of j omega at omega equal to 0 because delta omega is equal to 1 only for omega equal to 0, which you can therefore write as pi into x of 0 into delta omega plus 1 by j omega into x of j omega, which is the result that we have. So that is the result here. That is the accumulated sum integral minus accumulated integral, the running integral, rather we'll call it as the running integral from minus infinity to the current time instant t x of tau d tau is Fourier transform up to 1 by j omega into x of j omega plus pi x of 0 into delta omega. Okay. And then we move on to the next property, which is the modulation property. Modulation property states that if I multiply the signals in the time domain, so as x of t into y of t, then its Fourier transform is 1 by 2 pi into convolution of x of j omega and the y of j omega. So that's again proved in a similar manner, just like the convolution property. We call this as the modulation property because later when you study papers on analog communication, you will understand that if I multiply a signal by, let us say, cos omega ct, where this equal as the baseband, which is a low frequency, and this equal as the carrier, which is a high frequency. We call this process as a balanced modulation. It's called as balanced modulation. And the resultant wave you call as a double sideband. So I will not dwell much into the subject here. Double sideband suppressed carrier. So we will represent this in short as BSBSC. Double sideband suppressed carrier. So if I multiply a low frequency baseband, baseband is the information, is the signal that contains the information. Now it has to be transmitted. To transmit the signal, we use what is known as a carrier frequency. And this entire process, x of t into cos omega ct, is called as a balanced modulator. So you call this as double sideband suppressed carrier modulation because of some reasons that you will study in a communication paper, hopefully in the 5th semester. So x of t into cos omega ct is double sideband suppressed carrier. So in general, if I multiply x of t by y of t, then you call this process as a modulation, where y of t could be a high frequency signal and you can call y of t as a carrier that carries the information. Okay, so I will not discuss much about that. So x of t into y of t you call as a modulation. So that is what I want to emphasize. This is Fourier transform to 1 by 2 pi into x of j omega convolved with y of j omega. Proof is again straightforward. So I will represent x of j omega by the analysis equation here. 1 by 2 pi integral minus infinity plus infinity x of j lambda into e raised to j lambda t d lambda. I will use this lambda because I need to use omega outside this integral expression. So Fourier transform of x of t into y of t can be written as integral minus infinity plus infinity 1 by 2 pi integral minus infinity plus infinity x of j lambda e raised to j lambda t d lambda into y of t. So this is x of t into y of t into e raised to minus omega t dt. So what we will do is we will rewrite the integral as follows: 1 by 2 pi integral minus infinity plus infinity x of j lambda will take outside integral minus infinity to plus infinity y of t into, so here you have e raised to j lambda t, which you can write as e raised to j lambda minus omega into t dt d lambda. So if you look at this expression, if this had been just minus omega, this expression would have been y of j omega. Now instead of minus omega, you have minus of omega minus lambda. So therefore, minus of omega minus lambda is lambda minus omega. So therefore, we can write this as this integral as y of j omega minus lambda, right? So this is 1 by 2 pi integral minus infinity plus infinity x of j lambda y of j omega minus lambda d lambda, which you can write as 1 by 2 pi x of j omega convolved with the y of j omega, because this is a convolution expression. So therefore, this is proved. So this means that the multiplication in the time domain is equivalent to 1 by 2 pi times convolution of the individual spectra in the frequency domain. Okay, so we will stop with this and we will continue with the Parseval's theorem in the next class. Okay, thank you.